Hey Pioneers, great that you're here. Today we'll talk about Lucid, and without further ado, let's get into it. As per the GitHub repository About section, Lucid is a library that allows you to create basic Cardano transactions and write general off-chain code for your Plutus contracts in JavaScript. In addition to that, this library can be run via two runtimes, Node or Dino, of which the latter is a fairly new alternative for Node with some improvements. Given that Lucid is built in JavaScript, it allows you to easily write front-end applications with it, but note that you can also leverage it to build powerful back-end applications. You can install Lucid in the following three ways. Namely, you can install it for your Node application via npm install lucid Cardano. And if you use Dino, you can just import it via its web address. And if you directly want to inject it in your web app, you can also do that, of course. Lucid is completely open source, so if you want to tweak it or play around with it, feel free to build it yourself using the follow command in Dino. That's this one. And because Lucid is being actively developed, please note that the latest version that you have may differ from mine. Currently, the latest release is 0.9.6, but in this lecture we'll actually use 0.9.1, so note that. In this repository you can also find examples on how to use Lucid. These are located here. And another great source for learning and that lets you discover the possibilities of Lucid in a rendered version of the source code is actually via the Dino land web address. So if we go there, and I will change this to a 1, we have a rendered version of all the namespaces, classes, and types that Lucid offers. For example, we can go to data, and we'll see that data is defined as one of these things, which is closely related to the Plutus data type. In addition to being built in JavaScript, you can write Lucid code also with a TypeScript layer. This is also what we will do, since this is a good practice. In this week's lecture folder, I included two TypeScript files, lucidvesting.ts and seed.ts. Let's first take a look at lucidvesting.ts. Since I'll be using Dino as a runtime, we import Lucid via its web address location. Again, note that I am using version 0.91, and additionally I import the secret seed from the seed.ts. But as mentioned, we will see later how this is formatted. Next, we initiate Lucid as a constant Lucid. We use here the new method, and if we look at the rendered source code that's located here, this method requires a provider and a network. The provider here means a way to fetch and submit data to the blockchain, while the network indicates which blockchain. For example, mainnet, pre-production, or the preview network. Note that the question mark here indicates that these inputs are not needed. You can also initiate Lucid without it. Nice thing about Lucid is that you can quickly test and implement contracts due to it being easily connected to the blockchain via Blockfrost. This provider runs a full node for us, and via an API key that you can get on their website, Lucid requests data from the blockchain in various formats. Besides Blockfrost, it is also possible to connect Lucid to a provider that you completely host yourself. Specifically, it can connect to a combination of Kupo and Ocmius, but this is out of scope of this lecture. So here we define our provider, we initiate Blockfrost with our API key, and we define our network. Next, we will tell Lucid how to connect to a wallet. If we again look at the rendered source code, we can see that there are many ways to connect a wallet. These are the options. For most front ends, you want to use the select wallet method. This takes as an input a wallet API, and in short, this is an API that a wallet extension exposes if they are installed. To see this in action, you can try the following. If we inspect the code, go to the console, we can type window.cardano.nami.enable, and this is a function, and if we execute it, it will prompt our wallet for access, and it will return a wallet API. So we can give access. But since in this lecture we have an introduction to Lucid, we will not build a front end, and so we will select a wallet via a seed phrase. That is this function. And we will use our seed.ts file for this. Please note that you need to keep this phrase hidden. Sharing it with anyone will compromise all value in this wallet. Since this is a test wallet for me, it doesn't matter. And to showcase how this seed phrase is formatted, I will show a redacted version of mine that looks like this. So you export a constant of the secret seed with the words of the phrase. Now the stage is set and we can start running some examples. To execute this little file that we have, we will actually log the address of our wallet. So what we do here, we define a constant of an address, and this is of the type address, which is imported from Lucid, so it's a type. And what we do is we call Lucid and its wallet that we just selected, and we use the method address to retrieve it. We can easily run this via the following command, dino run -a, and then our file. If we do that, we see that it returns an address. The A flag here indicates that we allow the execution all access. To see what this includes, you can try running this command without the flag. So let's verify our address. If we copy that and go to the Explorer and we look at it, we can compare it to our Nami wallet and we can see that indeed it ends with S8. So we have the correct seed. Now that everything is set up, we'll use the vesting example of last week to write some off-chain code in Lucid. To start off, we will define the script as a constant vesting script that is of type spending validator, a script that is associated with an address. This script can be retrieved from week 3 in the folder assets under vesting.plutus. You can copy these things and paste them as such. Next, we derive the vesting address of type address from the utils namespace of Lucid with this function. Now that we have an address, we need to define the datum that we use in the script. We can leverage the TypeScript type system here and create a type that represents our datum. We define a beneficiary as a string and a deadline as a big integer. To see what you can possibly use from the data namespace from Lucid, you can open again the rendered source code from DinoLand, or you can play around in the Dino REPL. To open a Dino REPL, you can just type Dino REPL, and from it you can import Lucid as such. And it will ask for our permission to do certain things. And now it's imported. Then if we do l.data, the namespace that we use, we get back a whole list of things that we can use to create our datums. Again, we will not go into this too deep because it's out of scope of this lecture. But with it, you can create type datums in TypeScript. Next, we will create a specific datum, and the deadline that we'll use is this date that is already passed. so that we can create transactions easily and do not have to wait for it. We convert it to a big int via this as well. Then we have the beneficiary public key, which we can retrieve from our address that we just got from the wallet. We use here this function that is defined in Lucid. Next, from these details, we can get the payment credential and we can hash that to retrieve the public key hash as a string. Next, we fill in the blanks and define our datum as a vesting datum with the beneficiary and the deadline as mentioned above. Now it's time to create a transaction. In general, a transaction can be in one of three stages. It can be under construction, constructed but not signed, and lastly, it can be signed. These are represented in Lucid by these three classes. If we look at the first stage, we can see that we have the following methods at our disposal. For example, we can add a signer key to the transaction, which requires a certain address or public key hash, to be specific, to be added to the transaction. Or we can add a spending validator that is necessary if we spend from an address that is a script address. Or, for example, we can use the collect from method to specify which UTXOs need to be included as inputs in the transaction. If we go to the next stage, we have to close this stage first. To do that, we can use the complete method. This method returns a promise of the next stage. If we go to that stage, we see that we have the following methods at our disposal. And if we look here briefly, we have the options to sign a transaction with the sign method, but also to partially sign it so that we can share a witness that can be added later to the transaction. And again, to complete this stage, we can use the complete function, which again will promise the next stage, which is this stage. If we look at those methods, the methods that we have at our disposal are limited. We can only submit it or convert it to a hash or a CBOR encoded string. This concludes the stages that we have at our disposal. And now that we know the transaction workflow in Lucid, let's put this knowledge to the test in the vesting example. To log the funds at the vesting script address, I wrote the following function that goes through the stages of constructing and signing a transaction we just showed. It's called vesting funds, and this asynchronous function has as its input the amount of value that we want to lock at the address and returns a promise of a transaction hash if it's completed. Before we can stage the transaction, we convert our datum using our vesting datum type to a CBOR encoded string of type datum. That's done here. This CBOR datum string is a native, concise way of encoding our datum to send it over the network efficiently. And we use the data namespace here with the method to, and we declare our vesting type and our datum defined above here. Next, we initialize the first stage of creating a transaction by using the new TX method. In this constructing stage, we declare via the pay to contract method that we want to send something to the vesting address. We do that here. Here we also specify that we want to add our datum inline and that we want to send the amount of Loveless to this contract. Lastly, to go to the next stage, we use the complete method. Using the TX created, we then in the next stage use the sign method and complete it again to go to the third stage. In this stage, we simply submit it and await the transaction hash that it returns and return that as well to the function. To see it in action, we console log the vest funds function and let's send 100 ADA to our script. I saved it, and then I run this command. And what we see our address that we logged first, and we get a transaction hash back. If I copy that and go to our Explorer, notice that I'm on the pre-production network, we see the transaction. And if we look what happened, we see that our wallet took 2 inputs from our address and took those to balance the transaction and send 100 ADA to the script address with a datum that is inline, and the datum we provided is our public key hash and our deadline. And also it returned us some ADA that was return value to our address. So now let's look at collecting these funds. To collect these funds, I wrote another function that does something similar. It's called claim vested funds, which is again an asynchronous function, and it again returns a transaction hash or a promise of a transaction hash. Again, we define the CBOR encoded datum, and then we use Lucid and our provider Blockfrost to query the blockchain and see what UTXOs reside at our script address. We do that with the lucid.utxos add vesting address method, and it returns us a list of UTXOs. Now, it's not necessarily the case that these UTXOs all have this datum attached to it. So what we do is we write a filter that for each UTXO checks if the datum associated with that UTXO is our datum. And then it returns again a list of UTXOs. This list can of course be empty if our UTXO is not there, or at least there's no UTXOs with our datum, but it can also be multiple UTXOs because there can exist multiple outputs there with the same datum. Then we check if our list exists, and if it exists, that it's not empty. Note that these conditions needs to be checked because we have an await here, so it may not exist, and it may be the case it exists but it's empty, so that's why we do it this way. And if there's a UTXO to be claimed or more, we can construct a transaction. So we initialize the first stage with new transaction. Then we describe that we want to collect from the UTXOs that we just had indexed via our provider Blockfrost, and we provide a redeemer, namely the redeemer void, which is just an empty redeemer. Also, we specify that we want to add a signature, and specifically we want to add the beneficiary public key hash. Also, since we are expanding from a script, we have to attach the validator. We do that by this method and attach our vesting script. Next, we use the valid from to specify the transaction validity interval. And I use date.now, and then I subtract 100 seconds. Then to go to the next stage, we complete this stage. And similar to the last function we had above here, we sign the transaction and then complete it, and then we submit it and await a transaction hash. If in the case we didn't found any UTXOs that we can claim, we return no UTXOs found that can be claimed. So to see this function in action, we console.log await vested funds and save, and we run our function again. And we see that we get 2 actually back. Because I didn't comment out this console log await vest funds, it first sent a transaction to put another 100 ADA at the location of the script with that datum, and then it tried to claim funds that were already on the script address. So let's copy this line and go to our Explorer. And if we put in the transaction hash and take a look, we see a transaction has happened. And what this transaction did is It took some inputs from our wallet to cover for fees and to provide for collateral in the transaction, because we're using a Plutus script. And it took 2 inputs from the script address that had our datum in it, our inline datum. And it took our redeemer and it claimed the funds and returned them to our address. So it's a successful transaction. As a little recap, what we saw in this lecture was that we used Lucid plus Dino to create a small snippet of code to use the vesting contract. And the nice thing that we use is we use BlockFrost as a provider to query the blockchain so that we didn't have to install anything. I hope you enjoyed this lecture.